former Emeritus Professor and Deputy Director at the Liverpool School of Tropical Medicine in the UK. He is currently visiting professor at the Faculty of Tropical Medicine, Mahidol University. Professor Ward's research is focused on understanding the mechanisms of action and mechanisms of resistance to anti-infective drugs and novel drug discovery. He has published over 250 research papers and has established collaborative links with many academic organizations and pharma industries in the world. Without further ado, please welcome Professor Steve Ward for his lunch talk entitled Insights into the Mechanism of Action of 8-aminocunolene antimalarials.
Good morning, everybody. Can you hear me? Yeah. It's a pleasure to be back. I see lots of old faces that I recognise. It's another year, so it's another seminar, I suppose. This one's quite an interesting one for me to present. So, 35 years ago, I received my PhD. My PhD was on the pharmacology of proven. I was really quite excited about what I'd achieved in those 3 years, and then nobody really seemed to be very bothered the following 30 years, but I don't think any of the publications were ever cited. However, in the last 5 years or so, interest in proven clearly has erupted again as a consequence of its utility in proposed MDA elimination strategies. So, about the same time as everybody else started to get interested in the clinical utility of Primaquine in the elimination agenda, we decided to go back and start to have a look at the underlying pharmacology to see if we could pick some of the questions that had been left unanswered 35 years ago. I'm going to present some work now, and as you can imagine, after 35 years I don't do any of this work. There are lots of other people who generated the work. I'm just presenting the data for them, including Mamia, who's here, who's one of our Thai students who's been pivotal in these studies. So, I want to give you an overview of the work we've been doing in an attempt to address what has been a 70-year-old puzzle. It's part of a bigger initiative in Liverpool. The focus of this particular presentation will be to try and unpick what it is that's not that basic understanding. It's to find the basic understanding and utilise that to see if we can generate safer, more efficacious or better profile antiparasitics. So the whole reason behind this is for us to see if we can identify better 8-aminocunolene. Okay, so in terms of the structure, I'll give a little bit of background on the 8-aminocunolene. I'll say what we think is special about Primaquine. I'll touch on what we thought we knew about the mechanism of action, and then there are a number of questions that we in particular were interested in trying to address. So the question was, and I'll come to it later, metabolism is supposed to be critical in the activity of Primaquine and related 8-aminocunolene antimalarials. We were trying to identify ways of formally linking metabolism to the action. So most of the evidence to date has all been circumspect or secondary evidence. We were interested in this idea of transmission blocking activity from the concept that no matter how low you appear to be able to drop the clinical dose, you still appear to be able to get some transmission blocking activity, despite the fact that the species of metabolite that are suggested to be active are in almost non-measurable concentrations in that environment. So it's trivial levels of material which is having quite a profound biological effect, and we're trying to understand how that might be explained. And then obviously some aspects of the stage specificity we felt needed further interrogation. And as I said, the main reason for us to do this is to see whether there is space in the structure-activity relationships of the class, not just Primaquine, that would allow you to dissociate safety and toxicity and generate metrics. And the data I'm presenting actually has just been accepted for publication in Nature Communications. I'm not sure when it will come out, so if you are interested in this, keep your eyes peeled. It should be in the public domain in a few weeks' time. Okay, so why is everybody interested in Peruvian? I don't need to tell this audience, but it has two very, very useful attributions. One is that it can deal with relapse parasites, relapse malaria, because of its activity not only against developing liver stage parasites, but also against dormant parasites. And also it has this profound effect on late stage cancer blocking transmission. Interestingly for Peruvian, but not for all of antimalarials, its ability to kill asexual parasites is pretty weak. So several micromolar concentrations, pretty poor. So you can do it, but not in concentrations that keep the patient alive. So that activity is not a major contribution to its overall pharmacology. In terms of the history of Peruvian, so its structure was elucidated or described in the mid-40s by Elderfield. It was put forward as a safer alternative to pamaprin. Pamaprin, a drug developed by Germans at the beginning of the last century, originating from the method we were starting with. So a lot of work had been carried out with this particular class to try and generate molecules where they realised safety was the leading condition. And just to follow on from that, because I'll touch on it again in a moment, having been armed with Peruvian as a drug that could be deployed, was deployed with millions of people, and I'll say this relatively, it was seen as being relatively safe. The US Army continued their investigation of this particular class well into the 60s and 70s, and I've put David Jacobus here, who anyone who goes to ASTMH will often see him at the back of meetings on anti-malaria drugs asking some of the most potent and sharp questions despite his 95 years of age. And he was the main driver behind this program at the Walter Reed. They generated nearly 250,000 compounds in various structures, many of them were antimalarials. So, although everything seems to focus on Peruvian and maybe a little bit on pamaprin, there's actually a huge amount of biological data from which you can unpick structure activity information on this particular class. And here I've referenced to phenequin, a new kid on the block, a drug that's supposed to solve all of our problems in terms of MDA and safe eradication programs. Its characteristics, obviously it's related to Peruvian. It has a very, very slow elimination profile, maybe many days, which allows it to produce a single dose cure. It's claimed to be of low toxicity and has just received an FDA registration after more than 40 years. So you'll even find phenequin experiments in my thesis 35 years ago. So, as I say, it's been a long time coming, and I'll come to phenequin again later on. Okay, so what do we know about Peruvian? So, as I alluded to, its origins are nearly 150, 200 years ago with studies looking at methylene blue and similar compounds for anti-proteasole activity. It then led to a series of divergent analogues, which resulted in pamaprin, methylprin, and chloroquine. And obviously we will focus on Peruvian today, but clearly this particular structure activity medicinal chemistry initiative has generated some of the most useful compounds that we've ever had available to us in terms of the treatment and management of malaria infections. It's a drug on the WHO essential medicine list. In excess of 200 million doses have been given to man. Its importance obviously has been in the treatment of five-axis barley for radical cure, proposed for presumptive anti-relapse treatment, and then more recently this idea of transmission blocking of very low concentrations. And I've said here no reported clinical resistance. So there are reports in the literature about parasite lines which are resistant. They are asexual parasite lines that are resistant. They do not reflect the mechanisms that impact on liver stages and gametocytes, in my belief. It's a different mechanism that achieve micromolar concentrations, and people who allude to those as giving insights, I think that are on the wrong track to red out. So no clinical resistance as far as I'm aware. The major challenge has always been this side effect, which is the acute hemolytic anemia seen particularly in G6PD deficiencies. It's dose duration and G6PD deficient status dependent, although I think almost everybody receives improvement. So despite this particular characteristic, which I think for most drugs going through development now, including tafenoquine, except for a few tricks, you never get it registered. So you find it very difficult to get a drug with this characteristics registered today, although they managed to get tafenoquine without certain a few tricks linked to being able to diagnose almost perfectly that status and that risk. Okay. The one thing that we've always known is that primicrin, when you drop it on parasites in almost any in vitro system, does nothing. Even when you put it in some of the more sophisticated in vitro systems which do have metabolic activity in them, you still often see nothing. So most of the in vitro liver models of certainly with hypnozoitin, you fail to demonstrate potency with. So the idea that a metabolic step was essential in activity has been known actually for decades and decades. In actual fact, it was the core focus of my PhD 35 years ago. And together with lots of other investigators, the metabolism of primicrin has been investigated in a whole range of modern systems and in vivo in a whole range of organisms, including primates and man. And a whole myriad of different phase 1 and phase 2 metabolites have been identified. The one common feature, or a common feature with a lot of these metabolites is that they are very unstable. They are a nightmare, I can assure you, having spent 3 years trying to stably identify. They are a nightmare to characterize, they are a nightmare to work with. As soon as they are in solution, a lot of these start to unravel to other species. So trying to link a chemical structure with a biological effect has always been a bit of a challenge. Okay, for the work that we proposed to look at, we are focused on two sides of metabolism really. So the two main routes is this monoamine oxidase route to the aldehyde and carboxylic acid. We see that as a detoxification process. The carboxylic acid has restricted volume distribution with very little biological activity, at least in the work that we've done. And then there's a P450 dependent process which can generate a whole raft of different metabolites which have either been identified or inferred. You can get hydroxylation almost anywhere on that quinoline ring to some degree. You can get di- and trihydroxylated metabolites, then you can get these quinolinines which have been implicated in biological activity. So we've actually known most of that for the best part of certainly 35 years. And more recently has been an acceptance that cytochrome P452D6 appears to be a critical step, at least in part of the process. So this was part of our starting position, was to try and understand these important issues. And this is the data which I think supports the 2D6 argument. I'm sure most people in the room are aware of it. These are clinical studies using primicrin and measuring the incidence of relapse in the patient population where they genotyped or given a 2D6 score. 0 is 2D6 deficient, 0.5 is an intermediate metabolizer, and 1 to 2 are considered to be normal or extensive. And the observation was that the only time they saw relapses and multiple relapses within those patients that showed a deficiency in 2D6. So that seems to give pretty strong evidence that 2D6 was important, at least in some part of the process. Further confirmed by knockout studies in rodent systems where 2D6 is taken out, which again seems to implicate 2D6 as an important enzyme in the activation of antimalarial activity of this class of drug. Okay, the other thing which has been known for a long time, again since the time I did my PhD, was the fact that these metabolites are redox active. So as I said, there's data from my thesis which alludes to that, and this very nice piece of work here. Using hydroxylated metabolites and this Spanish ferridoxin reductase system, they were able to show the generation of peroxide quite clearly with a number of these metabolites. And this is just one image from the paper showing that you add the metabolite, this is oxygen consumption, sorry, in the system. You add the metabolite, you get oxygen consumption, you add catalase delivery of oxygen from peroxide, and you get oxygen released. It's dependent on having the reductase in there, it's essential to have the NADH in there, and this is just a control experiment. So it's been known for a long time that this is an important element of activity. So it's been suggested that this has been an important aspect of activity. So that historical evidence taken into account, we were then posed ourselves the question again, okay, so let's see what we can do to try and further understand the mechanism of action of recruitment. And the question is, can we link hydroxylated metabolites directly to antimalarial activity? Again, this question about relatively small circulating concentrations and quite potent anti-rheumaticide activity was something that puzzled us, as did the state specificity, and then obviously, does that give us information that allows us to make a safer alternative? So, what tools did we use to try and deliver this? So, obviously, many of you will know in Liverpool we have a very strong medicinal chemistry group fronted by Paul O'Neill, Professor of Medicinal Chemistry, and so his students were set the challenge of trying to synthesize some of these metabolites. They were particularly challenging for the students to do. They eventually managed to generate these species here. They are relatively stable as solids. They're relatively stable if we control their environment very, very closely. But we have to acknowledge that as soon as we put them into biological systems, we cannot guarantee that they are what they started off as. So we are taking a leap of faith that when we put the quinonamine into a solution, the majority of the biological effect is due to quinonamine or something which has arisen from the quinonamine than the structure which we don't know definitively. So that's one understanding that we have to accept. The second tool that we had was access to a liver model. At the time there was no Vivax liver model we had access to, and in fact the only validated liver model was a falciparum model by Sangita that we were confident had the right sort of controls. Now since we did the experiment, clearly there are lots of labs, including labs in Mahidol and in Thailand that have liver models and possibly have Vivax liver models where you can do these investigations. So we may wish to revisit some of these questions again with those models. Essentially, her model is a hepatocyte micropattern co-culture system. She adds sporozoites, they glide and eventually infect. They then mature and multiply, shown in the slides down here, and then start to liberate asexual parasites. So it's a tool that she had used and was able confidently to monitor at least exoerythrocytic replication antimalarial activity. And so we had access to this model. And then the second model was a live dead gametocyte assay developed in Italy by Grazia Mala, who eventually came to our lab to set this up. It's been used for several years. Essentially, if the parasites generate ATP, we get the luciferase reaction and a coloured parasite shown here. If we kill them, we can give them just a cytotoxic poison. Essentially, we lose the signal. So we measure the signal with or without drug. And obviously, as the ratio goes down, that's an indication of death of gametocytes. So we can measure dead gametocytes. So with those tools, with the probe molecules, with access to a liver replicating model, and with access to a gametocyte model, we can start to ask some questions. So the first question is, are hydroxylated metabolites actually responsible for antimalarial activity? And I'll focus first on this here. So this is in Sangita's falciparum model. And these are dose response curves. This is for peregrine. And in the blue line, this is using hepatocytes from a extensive metabolizer, 2D6 metabolizer. And in the black line, these are hepatocytes from the donor who was an intermediate metabolizer. And I think what you can see is that yes, we can get a dose response curve in both cases, but clearly the presence of effective functional 2D6 does increase potency by maybe an order of magnitude. So I think that further confirms 2D6 has been important, at least in the priming of the peregrine, before it biological activity. But if you look at the other metabolites that we looked at the system, first of all, you'll see that it's essentially independent of 2d6 status. Potencies in the two donor hepatocyte systems are essentially the same, and the potencies are roughly where you see the improvement in the 2d6 extensive metabolites. So I think this confirms 2d6, it confirms metabolism being important, but it does ask questions of whether 2d6 has any real role beyond the initial priming of primaquine to its primary hydroxylate metabolites in the humans. So then on to gametocytocidal activity, which is how we put our microbial prep, I will come into that. So heroic concentrations, so I'll leave that in a moment, I'll come back to it in a minute. So these are a series of our synthesized molecules. We're looking at gametocyte viability. In the red is in the absence of human liver microsomes, and in the blue is in the presence of human liver microsomes. And so I think it's pretty clear to see that hydroxy is pretty impotent even over long terms of incubation. Primaquine is pretty impotent even over long periods of incubation. It's only when you have the active enzyme system in there that you get biological activity. And here, with these molecules, you get an absolute kill in a relatively simple, very short period of time. What that said to us was that, and we've done this over a number of different time frames, although it is quite difficult because of stability issues, it suggests that gametocytes on their own, with either primaquine or the primaquine metabolites, are not capable of generating whatever it is that kills them. Or if they are able to do it, they can't do it very effectively. We were trying to link that biological activity with this redox argument and the generation of peroxide. So we tried to do this, well, we did this by using an oxygen electrode shown here. I won't go through the mechanism of it, but basically what it does is monitors oxygen levels, and in the presence of substrate we can see depletions, then gets peroxidized all the time. We had catalase and we see the release of oxygen from peroxide. And here's some data from a control, methanol. Red is primaquine, green is one of the hydroxylated metabolites, and blue is one of these 5,6 dihydroxylated metabolites. So they have different potentials to utilize oxygen and to generate peroxide, is our interpretation. And so we then try to link these two things together to see if the peroxide generation and the antiparasitic effect and the importance of metabolism went hand in hand. And so this is the data that I showed before, essentially the same, and you can see potency roughly tracks with the ability to generate peroxide as measured by this oxygen release. And we then went on to go and establish whether it was 2d6 that was the primary driving force of that. So again, red is controlled in the absence of recombinant 2d6. So note that the axes are different here. The enzyme activity in these systems is much poorer than the human microsomes. The red is in the absence of 2d6. The blue is in the presence of 2d6, and you can see clearly that 2d6 is doing something. It is enhancing the activity. But we then put this 2d6 inhibitor, paroxetine, in, and we would have anticipated that everything should return up to the red levels, or there or thereabouts, because at the concentrations we use, you should completely block 2d6 activity. And yet we don't. We only see a marginal recovery in the presence of the 2d6 inhibitor. And again, the peroxide generation measured by that oxidative burst in catalase tracks roughly with the potency. So again, that seems to be. But what confused us was the fact that we didn't get the level of inhibition by blocking 2d6, and 2d6 was really important. So our P450 system consists of the terminal oxidase, the P450 itself, and the membranes, but it also has this cyclone P450 reductase, which is quite a strong producing system to shuffle electrons through. So we had done lots of other work, in fact, Mahidol had done lots of other work with Plasmodium falciparum reductase, just trying to see if parasite reductase were able to generate these peroxides, and found that although they could do it very poorly. There was a prediction that CPR might be quite a potent reducing agent in this reaction. So we tested that out. And this is the data here. So this is using proven metabolite in the presence of human cytochrome P450 reductase, no P450. There's no P450 in the system. And essentially, red is control, blue is with the human cytochrome P450, yellow is in the absence of the NADP, and the green is pyruvate peroxide reduction. And I think it's pretty clear that the reductase on its own is pretty good driving this particular cycle, and it goes roughly hand in hand with the peroxide generated in the system. If you do the enzyme kinetics again, the kinetics seem to line up, so the ability of CPR to drive this reaction appears to be reasonably easily defined, and the ability to do it ranks alongside its antiparasitic activity. And then, can we show that at relevant concentrations during CPR, these metabolites can actually have antiparasitic effect? And again, so here we have dose response curves for primaquine, which is up here in the 2 or 3 micromolar situation. Then for these metabolites, with human CPR, we can see potencies in the hundreds of nanomolar concentration. So there's an argument that human CPR can actually drive these reactions to kill parasites, provided they're in the right juxtaposition. And this is just another experiment where quantitatively what we've been able to demonstrate, but importantly, we had to use 4-hour exposures, so that's quite a long time, is that with 1 nanomolar of 5-hydroxychloroquine and lower concentrations of 5,6-dihydroxychloroquine, you can generate micromolar peroxide. So it may well be that you get a slow poisoning of peroxide over time, and it may well be that different antimalarials have different rates at which they can achieve that. That might be intimately linked with biological activity. And so this is the model that was proposed by Giancarlo Biagini, not by me, was that provided you have plenty of NADPH, plenty of oxygen, and the CPR, you can effectively, over a period of drive, catalytically drive the oxidation reduction of this species to generate peroxide, and that's what is ultimately responsible for killing parasites. In terms of whether this is pharmacologically feasible, so this is data carried out by Ket Al-Jayusi, who's our PK/PD modeler, using human data and a number of assumptions which I won't go into, using data from a single dose 0.25 mg/kg and a repeat dose 5 mg/kg kinetic study, looking at the various predicted exposure in plasma and in the liver of the various metabolites. For our emetocyte activity, we needed to be in the 100 nanomolar type region to get activity, and for our livers, we need to be about 500 nanomolar. And the data suggests that at least quantitatively you're in the right ballpark, except the modeling assumptions that is made to put those curves. So when at least pharmacologically, you can argue that this is a credible argument. Why is primaquine selected against liver in asexual stages of the in sexual stages of the infection? So I think the argument for a liver stage activity is pretty straightforward. You see large concentrations of drug in the liver, the parasites are in the liver, there's lots of human CPR in the liver. You can make that analogy pretty straightforward. The argument for activity in circulating blood is a much more difficult one to argue. But when we were looking at the literature when we wrote this, a few papers came out that seemed to suggest that even fully mature gametocytes spend some of their time in bone marrow. So they're floating, they're not staying in the circulation, they're floating in and out of bone marrow and in and out of other organ structures, they're not just restricted to the circulation. So we did some, and bone marrow is quite a metabolically active substance, so we did some experiments similar to the ones before, using red blood cells as our medium as opposed to a bone marrow extract. And again, you can get oxygen depletion and you can get peroxide generation with the bone marrow aspirate. So an argument has been put forward is that there may be anatomical sites that the gametocytes pass through where the ability to generate these metabolites, these reactive species, occurs in an anatomical distance that allows them to have their biological effect. So there's a very crude mechanism. The argument is that the two-step process where cytochrome P452B6 generates these hydroxylated metabolites, predominantly in the liver. Then CPR, or a similar type of reductase, acts on these to generate peroxide, and the peroxide is having its effect on the parasites either in the liver or in the gametocytes. There may be other arguments for it, that's the one we're currently working on trying to demonstrate. So that's where we've got to. So I think in terms of primaquine, I think we have moved a bit further forward in terms of trying to identify what might be going on. So the question then is obviously is tafenoquine and just another primaquine, and then our ultimate focus is whether we can generate a safer antimalarials, safer than primaquine certainly, maybe even safer than tafenoquine, depending on how safe tafenoquine is. So, as I said quite early on in the process, primaquine is not that typical of the antimalarials. It's quite atypical. So if you look at the average activity against a whole range of Plasmodium falciparum strains of series of antimalarials, including tafenoquine, you see that primaquine stands out because of its lack of asexual antimalarial activity. Whereas lots of the others are quite potent. The argument for that has been suggested that tafenoquine can inhibit polymerization of humusone in the same way as chloroquine can. That is possibly the explanation, but actually you wouldn't expect it to accumulate the same way as chloroquine, so the fact that it would be as potent as chloroquine doesn't really hold that well. But I think the take-home message is that primaquine and tafenoquine do not always act the same. If anything, primaquine might be slightly different to the others. This is quite recent data, so it's been lifted from a paper which is widely quality. So it's a comparison of the need, the gametocytocidal activities of primaquine and tafenoquine in the absence of the presence of a drug metabolizing the system. And I think what you read from this is that primaquine requires activation, and tafenoquine doesn't. So tafenoquine is more potent in our system in the absence of a P450 metabolizing system. So metabolism of tafenoquine seems to reduce its potency, not enhance it. So again, some sort of difference. This is just taken from a relatively recent paper that's tried to collate and look at the metabolism of tafenoquine, and this is data that they derived using superzones, which are a mixture of high-level recombinant perceived cytochrome P450s and hepatocytes. And I think it's fair to say they tried to drive metabolism quite hard in these experiments, and they identified these particular species, which are interesting. So they identified a carboxylic acid, some side chain modified analogues, these diones. The important thing, two important things, I think. One is that the level of all these metabolites, despite driving the metabolism quite hard, are trivial. They're very, very low. Maybe not surprised, it's a locally used compound, so you might not expect that. The other interesting thing is that they could identify all of these species, all of those species in the control experiments. So there was no enhancement of the generation of these particular species by putting the enzyme system in place. So the question that's been raised is whether or not tafenoquine actually can reorganize or can reconfigure itself just without an enzymatic process. Chemically, that looks quite challenging, but that's something that we are trying to look at the moment. There are a couple of hypotheses of routes, but they would be far better delivered in the presence of an enzyme mechanism, even if the process of derivation is quite slow, which can generate species which would not be a million miles away from the types of species you get approved. So maybe some of the safety profile of tafenoquine is the fact that if it is being turned over to an intermediate that is active, it's being done very slowly. So that may well be protective in the case of the red cell, where maybe its ability to defend itself is better, whereas cumulative poisoning with a peroxide type end product in parasites may still be lethal. So that's where we are at the moment. We're actually developing these probes here which selectively knock out some of these alternatives to see if we can unpick whether there is some spontaneous rearrangement into phenytoin or whether a metabolite can be spontaneously rearranged in a way that will explain some of those early data. And then this is just data from a series of acetylminoquilines that we are working on now, and I think the take-home message is that we can generate acetylminoquilines knowing with a knowledge of the SAR that certainly don't require metabolic activation to exert their effect, don't require 2B6 to exert their liver effect. And we're in the process now of trying to get a robust in vitro system to monitor hemolysis. Data to date has been really quite disappointing. It's reproducibility we are finding to be quite an issue. So if you have some of these assays looking at the PLA, welcome some discussions to see if we can actually try to divorce the antiparasitic activity against the hemolytic activity. The argument being that if it's about rates and routes of metabolism, it may well be that you can increase the therapeutic index with the knowledge of that particular process. So, the conclusions then is that proven activity in terms of its activity against liver and erythrocytes does require activation by 2B6, but the metabolites in the quinones are pro-oxidants and don't require 2B6 to do any more problems. Importantly, we can demonstrate that the process is potentially catalytic, so you don't need a great deal of material that you've got the bioproducing system in there to generate very high levels of a potential toxic intermediate peroxide. We've shown that human CPR can characterize that site within the liver and possibly in the bone marrow, so it may well be that the process is not parasite driven. The final part of the process may be host driven. So phenytoin, there may be commonalities in the way in which it exerts its effect, but there clearly are subtle differences, and it may well be that those subtle differences do lend some support to the argument of maybe better safety profiles. And the question of whether we can develop acetylminoquinones that we can separate the hemolytic activities from activity, we think is possible, but there's a way to go yet before we can actually demonstrate. So a nice picture of the Mersey before I answer any questions, and then finally just to as I say, I don't do any of the work anymore, I just come to Thailand and tell you about it. In Liverpool, the main driving force has been Giancarlo Biagini. Mhawao sat in the audience, did some of these experiments as part of their PhD. All the medicinal chemistry is driven by Paul O'Neill's team. Obviously, MIT provided support with falciparum, liver assay. David Baker has been helping us with erythrocyte cultures, and Pietro Alano and Grazia, who